I will assume you're comfortable with all these ideas, but even if you haven't come across some of these, that shouldn't affect your understanding for the rest of the video, because there's nothing too serious coming. For the first half, I will remind you of around 5 old high school problems and then their solutions, all of which might initially appear disconnected or pointless, but then, towards the end, I will hopefully unify everything to discover some order in the entire chaotic jumble. We will also learn an often overlooked lesson from an old chestnut. So, at any point, if you don't get where this all is going, or how it makes sense for all this to be in a single video, or if everything appears tasteless for some time, please bear with me. I hope this finally brings an unexpected smile on your face. So, let's consider the simplest polygon, a triangle, simple as it has the least number of sides. A cool fact about any triangle is that its sum of interior angles is always 180 degrees. But do you remember finding this result starting from the fact that a triangle is nothing but a closed figure bounded by 3 straight lines? Well, we could just sandwich any triangle between parallel lines as such, and you see, these angles A, B, and C must sum up to 180 degrees. But I kinda want to bring these angles A and C into our original triangle. Or if that doesn't make full sense, I want to use my construction for our original problem. And here's how. Because of the rotational symmetry of these Z-like figures, the angles which are colored the same must also be the same size. And because that means all the 3 angles of the triangle are congruent to the angles in which the 180 degrees are split, our proof is over. Nothing too amazing so far. Now consider factoring the expression x to the power 4 plus 4y to the power 4. Here's how I would go about factoring this. I see the square of 2 terms added together. So why not try completing the square by adding and subtracting this? And very soon, our original expression is factored by using the difference of squares formula. Let's also tackle this complicated looking integral. We will use Feynman's famous technique for that. So we introduce this new parameter t and then differentiate our integral with respect to this new parameter in the following fashion. Without going into too many technical details, which I will leave as an exercise, let's just say that we arrive at this new integral, which can be easily evaluated doing integration by parts. This gives us a separable differential equation for I of t, and upon separating the variables and integrating, the explicit form for I of t turns out to be this mess. Now remember what the original I was. We put t is equal to 1 and get this final answer. Do you remember how we classically reach the definition of electric field strength everywhere in the space due to a point charge? Let's imagine how we could go about encapsulating our visceral intuition for the cause of electric forces into an equation. We can smell that the concept of force somehow has to be involved. But we can evaluate the electric force between 2 particles using the Coulomb's law, whereas the electric field, whatever the expression for it may be, has to involve only a single charge. So we make the number of particles 2 by bringing this this charge into our picture, and use the Coulomb's law to define the electric field at any point by dividing this force by the small test charge little q, so that we can pretend as if the test charge never existed. Many old math stories or puzzles are not at all taken seriously nowadays, perhaps due to the enormous number of times these have been repeatedly told and heard in math classrooms, or in the streets, or on YouTube, or somewhere else on this planet. Consider one such deceptively simple riddle that I suppose any puzzle enthusiast would have come across and even had the solution instantly. But trust me, the real part begins after the riddle. Even though there are many ways to go about solving this, I will take the following. A half, a third, or a ninth of 17 aren't integers, and you can't kill the goats because they won't be happy this way, obviously. So you add your own goat to reach a total of 18 goats. Then all the relevant parts of 18 are whole numbers, and the sons in total get 17 goats, with each one getting more than what he should have initially gotten, so all are happy. And you walk away with the goat you initially added, so you are also happy. This old and modest seeming riddle actually contains countless germs of generality. And to understand that, let's recall what we just did in this solution. There was a difficulty initially, namely the relevant parts of 17 were not integers. Obviously, we couldn't deliberately start calling 17 over 2 or 17 over 3 an integer, and even if we did, that wouldn't be of great help. So to solve our problem, we introduce something clever from our mind, namely the 18th goat. But to ensure that by doing so, we didn't change the problem itself, we took that piece of cleverness back at just the right moment. Now here is the catch. In essence, we do exactly that in mathematics all the time. For example, those parallel lines were actually the 18th goat for our triangle problem. And once we reached the desired result, we didn't need the lines anymore. Same here. In this case, this term 4x squared y squared was the 18th goat, which we added and then subtracted. In the integration problem, this new parameter t was the analog of the 18th goat. And while we were differentiating and integrating by parts and all that, in some world, in a sense, the goats were getting distributed among the sons. And finally, when we substituted 1 for t, we took our goat away. While defining the electric field strength, we needed 2 particles to calculate the force, just like we needed 18 goats to be able to distribute them. So we made the number of particles 2, just like we made the number of goats 18. We had to ensure we didn't change the problem itself. We had to ensure that the resulting expression must have been independent of little q. So when we divided and finally took the limit, we actually took back our goat. After all this, you might have started to think one requires this innate dreamy skill, these germs of cleverness in his or her mind to find these cousins of the 18th goat. But rather than just thinking of cleverness as the source of this 18th goat, I want you to also see that these cousins of the 18th goat, like the charged little q, the t, or the parallel lines, these cousins are what really manifest themselves as what looks clever to us. And while this video consisted just the tiniest fraction of all the cousins of our celebrity, it is needless to say that sometimes even the old and elementary stories can augment our perspectives. But if we take this a step further, it's not that all this is only about, say, doing math exercises or solving textbook problems. Not only do we often do this in math, this is an aesthetic point of view, a way to approach what the subject itself is and how it behaves. For instance, the jump from our physical world to the mathematical reality, and then somehow coming back into our physical world with some explanations for what happens, is also analogous to introducing the 18th goat and then taking it back, just so that our problem is solved. As an illustration, in classical physics, when we want to talk of position in space, we introduce a coordinate system. That coordinate system here is the mathematical reality that we introduced like the 18th goat. This mathematical reality, these germs of cleverness, aren't they amazing?